Okay, so welcome back, everyone. So today it's our pleasure to have Peter Giesl, who will be talking about solving differential inequalities with applications to complete Lyapunov functions. Yeah, thank you, Peter.
Thank you, Boumediene, and welcome everyone. So my talk, I'm basically trying to uh, get the connection between some numerical methods, kernel methods, and dynamic systems. So yeah, and I should mention my collaborators Holger Wendland, Stefan Suhr, Sigi Hafstein, and Carlos Argaez. Um, so my first part is in the kind of mesh-free collocation world. So I'm going to start and talk about how we can solve differential equalities equations first with mesh-free collocation, and then how we use that and extended this to solve differential inequalities. So the first part is more on that side, and then in the second and third part, uh, I'm I'm going to apply this to dynamic systems and use that to compute completely Lyapunov functions. And basically, the third part is just a little twist on that, how we can do this even better. And I will introduce completely Lyapunov functions if you don't know exactly what that is in the second part. But so the first part really is, I want to start by telling you basically that's kind of 20, 30 years old, how to use mesh-free collocation in reproducing kernel Hilbert spaces. And then I'm going to introduce how we do that for inequality. So these first two slides are really relatively old stuff, and it's not stuff that I've done myself. So the goal is to solve LV is R, and L is a linear operator. You can think about it as a linear differential operator. So this could be a PDE given right-hand side and given linear operator. It doesn't have to be a PDE. It could be some other linear operator, but think about it as a PDE. It needs to be linear though. You can include also different operators. You can include boundary conditions as well. So it's quite flexible. But for the moment, we just think about just one operator L here. And we're going to solve it in a Hilbert space, and actually in a reproducing kernel Hilbert space, H. So the function that we're looking for, V, is in this set H. And it's a reproducing kernel Hilbert space with a kernel phi. And this is just the definition of a reproducing kernel Hilbert space. So the kernel has two arguments, x and y. If you fix one of the arguments, it's a function of the Hilbert space in the other variable. And the reproducing properties, if you have any function f in the Hilbert space, you can write it as f in a product with the kernel. And this is the x, that's one of the arguments here. And basically, there's a one-to-one relation between kernel and space. So if you have the kernel, you have a space, and if you have the space, you have a kernel. The kernel I'm going to use are the Wendland functions. They are functions of the absolute value, or the norm of the difference of x and y. So this is now a scalar, a positive or non-negative scalar rather, and these are functions. These psi k's are polynomials, and they have a compact support. Usually it's 0, 1. You can scale that obviously if you want to, and the k. So it's a whole family, and the k defines the smoothness. So depending on k, you have smoother functions, and that in turn leads to a smoother Sobolev reproducing kernel Hilbert space. So the corresponding reproducing kernel Hilbert space to these kernels are their norm equivalent. So they're not the Sobolev spaces with a normal norm, but they're norm equivalent to the usual Sobolev spaces. And here the k is, you can choose by choosing the kernel, and then there's a d plus 1. D is the dimension of the space. So that's the setup. And how do we, so what we want to solve is actually this differential equation in this space. And how do we do that? So we formulate this as a minimization problem. So what we really want to solve is this PDE, LV is R, and amongst all the solutions that you can think of, we want to find the norm minimal solution in H. So the solution V that minimizes that. And now we can discretize this problem. So basically this problem 2 and 1 are look very much the same. The second one is basically just we make sure this equation holds at specific discrete points. So we choose our points X in omega. They only have to, they can't be the same points. And the only other condition really is that they are regular in the sense that if you apply the operator L and then plug in the point xi, then that's not 0. So it's basically not singular points of the operator. And they can be, it's Meshfree, so basically they don't have to, they can be scattered as you like. And so we are now going to solve this discretized problem. And the solution of this problem is very easy to compute. It's basically this formula here. It's a linear combination of these functions. So what are these functions? If you see this for the first time, it looks a bit scary. So the phi is the kernel, arguments x and y. The x is this x. And what we do now is we apply lambda. So lambda is lambda I is, we apply our operator L, or think about this as some differential operator, and then we replace y by the point xi. Yeah, so basically if this was just a derivative, you take the derivative of phi with respect to y, and then you replace y by the point xi. You multiply it with a weight factor alpha, and then you sum over all your collocation points, and that's your function. Now, the only thing you need to find out is what are the alphas, and the alphas you can find by making sure that these conditions are satisfied. So basically you plug this into your conditions here, and you end up with a system of linear equations, which is this one. A alpha is R. R is the right-hand side at all the collocation points, and the matrix A, there you apply this operator once with respect to y and once with respect to x. So you get a matrix, an n times n matrix, where n is the number of collocation points. It's automatically symmetric. And with these conditions that we had earlier, it's actually a positive definite matrix. So this system has a unique solution. So practically all you really need to do is you fix your kernel, you fix your collocation points, you compute A, you compute R, then you can solve this system of this system of linear equations, get alpha, plug it in, and you have your solution. And obviously it's an approximation of the solution of this problem because we've discretized, but there are error estimates available that the solution of the discrete system and the continuous one, this one approaches the other one if it exists, and you can even get error estimates depending on the smoothness of K, for example, and they depend on the fill distance of X in omega. So basically how dense you have distributed your points in omega. So that's basically the existing theory for equations, and what we wanted to do, motivated by the application of dynamic systems, we wanted to look at inequalities. So what we want to solve is basically this here. So we have some points in omega that I call in the set gamma, where LV is equal to R. So that's like the previous problem, but we have some points, some area, which is omega without gamma, where we have an inequality. And one could be the empty set, so you could just have inequalities. If you just have the equality, we're back to the old problem, obviously. But later, we wanted to look at problems where we have some points or some area of omega where we have equality conditions, some inequality conditions. And we basically wanted to do something similar. And this is what we came up with. So N is the same linear differential operator, B and R are given, they're continuous functions, and we want to consider a solution in a reproducing kernel Hilbert space again. So again, what we're looking for, we are actually looking for a minimizing function with this property, which is now even more important because we have this inequality. And the idea is, well, now it looks very similar. That was why I introduced you to the equality problem first. So we take this continuous problem and we discretize it. So we have, again, discrete points. They are regular in the sense as above. We have one set of points in gamma, which I call x gamma, and one in the rest, which I just call x omega. So I've just discretized these conditions. So now thinking of the previous approach, the questions we wanted to answer are, do both problems, the continuous problem 3 and the discrete problem 4, do they have a unique solution? Hopefully they have, and they will have. How can we compute a solution of this problem? And then are there any error estimates, or at least a convergence of solutions of this discretized problem to the continuous problem? And I will present solutions to all of them apart from the error estimates. So at the moment, the only thing we could prove is strong convergence in H, but we haven't been able to quantify that in error estimates. So that's still something to work on. Right, so let's go through these points. So the discretized version is this one. So I've just rewritten the discretized version, but I've now used these lambdas again. So in our case here, these lambdas are just the operator L again and plug in the point xi. So this here, LVxi is just written as lambda I of v. That's basically the same thing. It's just handy to write these lambdas here. So the first statement is this problem has a unique minimizer, and we are able to write down what it looks like. It has exactly the same form as in the previous case. So we sum up over all these functions with some alphas. We sum up over all the points. So remember, the first m points are connected to the equality conditions, and the following n points are connected to the inequality conditions. But this time we are not solving a system of linear equations, which would have been the middle line here beforehand, but it's actually a quadratic programming problem. So we have a matrix A, which I will introduce in a minute, and matrices A1, A2, and the R and the B, which are again just the vectors here on the right-hand side. But this time it's a quadratic minimization problem for alpha, where this is minimized subject to these equality and inequality conditions. And the matrix A is precisely the same matrix as before. Yeah, it's constructed in the same way. And A1 and A2 are just part of this bit matrix A. It's basically the first m rows and then the next n rows. So basically you just need to compute the matrix A again. The right-hand sides are R and B, but this time instead of solving a system of linear equations, we're solving a quadratic programming problem. So it's a bit more effort to do it numerically, but not that much. It's quite straightforward. So let me explain how basically we're going through all these steps. The first one, just give a sketch of the proofs. The first one is why does this have a unique solution, or at most one solution at this point. We're going to show that it has one later, and that's kind of a standard way to show this. So we start with two functions, s and v. S is the minimizer, and v fulfills the constraints, and we want to show this this inequality. How do we do that? Well, we assume it's not satisfied, so then SV minus S is negative. We take an alpha between 0 and 1, and we look at the convex combination of V and S. That automatically satisfies the constraints because it's a convex combination. And then we look at the norm of this and calculate it. And if this here is negative, then for a positive alpha, this will be strictly smaller than S, but that's a contradiction to S being the minimizer. So if S is the minimizer, we have this inequality, and now we assume we have two minimizers. calculate this here, and for both of them we can use this inequality and can show that there's at most one minimizer. So yeah, it's kind of a standard way to prove these things. Now, the other thing is that this problem 6, which I restated here, is with our quadratic problem, has a unique solution, and mainly that's due to the fact that the matrix A is symmetric and positive definite. So we have the objective function has a minimum, basically. So that's quite straightforward. And the interesting bit that I also wanted to sketch, because I think it's quite nice and draws in the theory from the equation point, is that the unique minimizer is of this form. So at the top you can see the formula for V star, and we want to see that this V star is the minimizer. So what we assume is we take some other V that satisfies the constraints, and then because V star is the minimizer, we want to show that the norm is strictly or is smaller or equal than the norm of this V. And the idea is basically we have a different function V tilde that we will show as a norm smaller than V but larger than V star. So we basically put this in between and show that that would show that the norm of V is really larger than the norm of V star. So how do we get this V tilde? So remember that the V satisfies the constraints. So the constraints are here the equality constraints, and here the V would satisfy this here is smaller or equal to B. So it has some values that we call B tilde that are smaller than B, and we just fix those and call those B tilde. Now, this is the problem that V satisfied, and it's an equation rather than an inequality, just because for this particular V, we fixed the B tilde. Now we can ask ourselves, what's the norm-minimal solution of this problem? V is obviously a solution of this problem, but it might not be the norm-minimal. And because this is an equation, we have the theory from the start, and we know the norm-minimal solution of this problem is of this form with some alpha tildes. And it's norm-minimal, so the norm of V tilde is smaller than V. Now we have something, the V tilde, that is of the form that we want, that our V star is in. So now we can compare those two. So both these are of this form, just with different coefficients. One has the alpha tilde, and one has the alpha, basically. But then we can use that this here is minimized. So that was, if you go back here, we found our V tilde so that this here is minimized. But this is, if you calculate, nothing else than the norm squared in H. So basically, because the V star minimizes this, it minimizes the norm, and we have the other link. So now V is in norm larger than V tilde, and V tilde is in norm larger than V star. So we have shown this norm minimality. So I just wanted to show this because it was a nice way of connecting the theory before. But so I don't know how much you're into proofs. That's probably the last proof I'm going to present. This is a big theorem, but I won't prove it really. So the theorem, you don't need to look at the details. The theorem basically tells you that the discrete problem, the solution of the discrete problem, will converge to the continuous problem, and it's done in more detail. So basically, you have a sequence of approximations somehow to the continuous problem. You have a sequence of discrete problems that we can now solve, and the sequence is basically determined by the collocation point. So these are mn in step n. You have mn collocation points in omega in gamma, and then you have the nn collocation points in the other one, and you will have more and more of them. That's the second point here. The fill distances of x and gamma in gamma, and then x omega n in omega, will converge to 0. So we get more and more points, and then if Vn are the solutions of these discrete points, of these discrete problems, then the Vn's converge strongly to V, which will be a solution, the norm-minimal solution of the continuous problem in H. Yeah, so it's basically just lots of details, but it really means discrete problems with more and more points in there, the solutions converge to the solution of the continuous problem. The assumption is that there is a function that satisfies the constraints. Otherwise, you won't be able to prove anything, but then you can have the VNs converging to the normal solution. And I just quickly sketch the proof is relatively straightforward. You'd start with this V naught that is satisfies the constraints. So the solution, it also satisfies the constraints of the discretized problems, obviously. So the norm minimal ones, Vn, have a norm smaller than that. So you have a bounded sequence. So a subsequence will converge weakly to a limit V, and we have this here. And then basically we need to put in some work to get the other inequality here to show that the Vn's really strongly converge to V. And that's basically done by lifting all by basically showing that these constraints are satisfied for the weak limit, and that's using the kernel representation, and that we have closer and closer collocation points where we can use the corresponding ones for Vn. Yeah, so I basically leave it there. It's relatively straightforward. So before we go to the second part, basically let me go back to what we've done. So we are now able, we have a numerical method that we can solve mixed equality and inequality problems, and are able to compute approximate solutions to these that get closer and closer to the norm minimal solution. And now we want to use this in an application, and the application will be in dynamic systems, complete Lyapunov functions. So what are complete Lyapunov functions? You consider an autonomous ODE x dot f of x, which defines a dynamic system, and you think about the long-term behavior. So the phase space can be split into two parts. One is the chain recurrent set. That's where all the equilibria, periodic orbits, attractors, repellers, everything is in there. Something that is more or less recurrent. And then is complement. The complement has gradient light flow, so basically it just passes through to the chain recurrent set. And you can characterize this by a complete Lyapunov functions, which goes back to Conley in the 70s, 80s. Conley's function is actually not, it's only continuous, it's not differentiable. But if it was differentiable, then this function would characterize these two parts by its orbital derivative. So the orbital derivative V dot is the derivative along solutions. So the part where V, the function, is decreasing along solutions, that's precisely the gradient-like part, or the transient behavior where you go through. And then where V dot is zero, so basically constant along solutions, that will characterize the chain recurrent set, and the different values of V give you different chain transitive components. So basically what you need to think of, and have I got a picture? No, the picture comes late. But think about V decreases, that's where you go through. V is constant, that's where we stay. So if we are able to compute, if I give you a system x dot equals f of x, and you're able to compute a Lyapunov function, this Lyapunov function will give you a lot of information about the system behavior. So the goal will be to find a complete Lyapunov function. And I write candidate complete Lyapunov functions because it will probably be not as good as a complete Lyapunov function. I will explain this in a minute. So basically, what is a complete Lyapunov function? It's something where the derivative, the orbital derivative, is either 0 or negative. So it's smaller or equal to 0. And I can tell you a function where V dot is smaller or equal to 0 for any system, just take the constant function. Yeah, that doesn't tell you much about the system. So if you have more areas where it's really decreasing, you get more information about the system. Because the part where V dot is 0 contains the chain recurrent set. If everything is V dot is 0, then that certainly contains the chain recurrent set, but it doesn't give you much information. So the more areas we have where v dot is negative, the better. And you can also see that the maxima and minima can give you information about stability and so on. So here's my little sketch. Just if you've never seen this, it gives you some information. So if this was your function v dot, so the derivative of v, and this was your function v itself, then without looking at the system, you can see that the point, so v dot is really negative or zero. Where it's zero, there are just 3 points. These are parts of the chain recurrent set. So in this case, it's just 3 equilibrium points. And then if you look at v, you know v must decrease or be constant. So basically here it must decrease, so the dynamics go right, and here they go left. So that means this will be a stable, asymptotically stable equilibrium point because it's a minimum. This is a maximum, so solutions would go the other way. So this is an unstable one, and this again is a stable one. So basically, by a combination of looking at the derivative, where is the derivative 0 and where is it negative, plus whether these are minima, maxima, or saddle points, you can you get a lot of information about chain recurrent sets and their stability. Right. So it would be good to do that. And I've been working on these numerical construction methods for some time, and you can you will see in a minute how this solving differential equalities or inequalities comes back in. So we want to find a function where v dot is negative or 0, ideally negative. So the most naive approach would be, well, can we solve this problem? Find a function v where the derivative is -1. That would mean it's decreasing with constant rate -1 everywhere. And that is actually a PDE. So the v dot, although it looks like a normal derivative, is actually a partial derivative. Now, on the chain recurrent set, this can't have a solution. Yeah, think about an equilibrium point. There the old derivative is 0. So it won't have a solution on the chain recurrent set. You can still use meshless collocation, as we did, as I introduced at the beginning, and try to calculate a solution. This continuous problem doesn't have one, but if you discretize it, we can still compute a solution, an approximate solution. And we can then say, well, the set where this is approximately 0, maybe that is a good approximation of the chain recurrent set. And so we've done that. We can't use really any theory because this doesn't have a solution. But if you just, so we have no proof of convergence or whatever. We've tried some iterations for better approximation, but the results computationally are quite nice. So basically, this is the system. We've basically used the Meshfree collocation to approximate the solution to v dot is -1. So this is v dot, gradient b times f. And as you see, it's mostly -1, as we've approximated it. But where the chain recurrent set is, it can't be -1. It can't decrease on a periodic orbit, for example. And you can basically see clearly it's only not -1 where it is forced not to be. So you can basically draw a line and say, if you're near to 0, you get these points, and these are precisely good approximations of the chain recurrent set. So the system actually has 2 periodic orbits, one here and one there, at an equilibrium point here. And the function itself looks like this. And remember, maxima are unstable because think about a ball rolling, it has to roll down like in a roulette. So you can see that this periodic orbit here is stable, asymptotically stable. This one is unstable, and then if you could look inside, it will have a minimum in here. So this equilibrium point is stable. So it does a good job. It calculates a complete Lyapunov function, or at least a good approximation of it. That tells you a lot. But there's no theory to actually show what it does, because we are approximating the problem we're trying to solve doesn't have a solution. So that was quite annoying as a mathematician. So what we try to do is we try to solve a problem that actually has a solution. So that's why we came up with this one, and now you can see why we were interested in solving something that has equality and inequality constraints. So this fits into the framework I talked about in the first part. We want to find a function where v dot, and that's a linear operator applied to v, is -1 for some area, and it's smaller or equal to 0 for the other area, or actually for everything, if you want to say. So basically now we allow for chain recurrent sets. Basically we need this for all points, but we also want to make sure some points actually have a negative derivative. If we just get rid of the first line and only look for a function where v dot is smaller or equal to 0, the minimal solution is, again, v is just constantly 0, and it doesn't tell us anything. So we could do that, but we don't get any information. Now, by forcing the function to actually have some parts where the derivative is negative, we at least get something non-trivial. So first of all, for this to have a solution, we need that this set gamma needs to lie in the gradient flow part. If we happen to choose the gamma in the part where it's actually 0, then again, it doesn't have a solution. So the question immediately is, how large does this set gamma need to be? And the minimal set you can think of is just 1 point. So we actually will show you examples where this is really just 1 point, and for the other points, we don't specify whether it's 0 or -1 because we don't know. We want to find out. And that already gives us a really good approximation again. And the other question is, remember that one assumption in our theorem was that there exists a function that satisfies the constraint. So does there exist a complete Lyapunov function which is -1 in the gradient flow part? Can we prescribe this? Because Condi's theorem doesn't do that. It only actually says it needs to be continuous, and it doesn't specify for that reason that we have a specific rate of decreasing. So that question answered first. So we have proved a theorem that basically tells you, yes, you can fix the derivative on the gradient flow part. So let's go through it in detail. So we have a dynamical system with a certain smoothness L. And if we take any compact set in the gradient flow part, so this is omega without the chain recurrent set, which is the gradient flow. And if you take a compact set within that, and you specify any negative function here, then you find a complete Lyapunov function that is exactly G on this set K, and is still strictly negative on the remaining bit as well. And it's basically a modification of a complete Lyapunov function without any conditions, and we basically managed to set it, so it's quite technical, the paper, to whatever function G we want. So in particular, we can choose G to be -1, and then we can, such a function exists if the gamma is a compact subset of the gradient flow part. So that's good news. So we can use our theory, and we actually have guaranteed convergence. So here I show you 2 examples. So this is the same example that you saw earlier, and I didn't actually write down the equations before. So these are the equations. So we have 2 periodic orbits and the equilibrium, which is stable here in the middle. And you can see it looks very much the same as the previous picture. This is V. It has a maximum here on the inner one, a minimum, which is hard to see in this picture, around here, and then a minimum here at the equilibrium point. And this is the orbital derivative V dot, and you can see it's not that clear to see here, but you can basically cut it off near 0, and you will find again these two circles here. You see this kind of outlier. This is the 1 point. So if you go back to this one, we only fixed the derivative be -1 at exactly 1 point, and the other conditions on all the other points were just smaller or equal to 0. So at this point, was fixed to be -1, because it's norm-minimal in this Sobolev space, it tries to get to 0 as much as it can, with still satisfying this condition. So that's why it's all a bit on a smaller scale. And again, here you can see the function v is also, the norm of v is just much smaller than it was before. So yeah, this is the point with the equality constraint. Here's another example, which has this time a homoclinic orbit, but it's still attractive. So we can't see that it's homoclinic, but we can see that it's part of the chain recurrent set, which is here. And here we have an unstable equilibrium point at the origin. And again, we have fixed this one point with the derivative -1. And you can see, again, here the derivative is 0 and here as well. And the last part I want to talk about is, so basically, it works nicely numerically. We now have a proof that our approximations will converge to the solution, because there is a solution. You still need some information in there. So let me go back to this one. So if you look at this problem, we still need to know that the gamma here, even if it was just 1 point, is not in the chain recurrent set. And kind of conceptually, it would be nicer if we don't need to put any information in, because basically we want to get all the information out. We want to find a complete Lyapunov function that then tells us what are the dynamics of the system. So it would be nice to have a problem that we numerically solve that just gives us the complete Lyapunov function without any prior information. And as I said before, the first idea would be just look, we want v dot to be negative or 0, so that will be requiring no information. But as I said, the norm-minimal solution of that one is just v equals 0, so it doesn't give us any information. So we want, as I said, we want areas where v dot is really negative, and we want to reward that. And the idea was, well, instead of putting it in the constraints, we put it in the cost function here in the minimization problem. So let's have a look at this. So we still need that v dot is smaller or equal to 0. We need that, but we want to reward areas where v dot is negative. Yeah, so the v dot is anyway 0 or negative. So this is smaller or equal to 0. And the more negative it is, the better, because it minimizes this. Now, this is an integral. It's obviously it could be some areas where it's very negative, or it could be lots of areas where it's a bit negative. So it's no guarantee that we find the best Lyapunov function, but at least that's an idea where we have no information about the system in the problem. This is basically a problem where we need no information about the system itself. Yeah, so this cost function here rewards areas with negative orbital derivative. We don't need any knowledge of where we have a gradient flow, like flow or anything about the system, and it will still lead to a quadratic optimization problem. So if you go through the steps, which I'm not going to do in detail, but you can follow the same steps as before, this continuous problem is the one I showed you, and if you discretize it, this term here becomes basically you just do some Riemann integration. Yeah, it's the simplest form of discretizing this integral is this one here. The w. So basically, instead of points, you now split your area into small parts with a point in there, and the wi is the volume of that particular area. So that's basically the discrete problem that we want to solve. And if you now try to find a solution for that, then you see, again, as I said, going through the same ideas, it has a unique minimizer v star. The v star can still be written in this form as before. And it's a solution of a quadratic programming problem where this new term here becomes this term here. So basically, this is quadratic in alpha. This is kind of linear in alpha. The w corresponds to the wi as before, and these are the constraints. So it's it's basically it's the same type of problem, and that's another reason why we got this integral formula in there, because it's a linear term. So the overall it's still a quadratic programming problem for alpha. So we can solve it in the same way as before, and we have the same theorem that the solution of a discretized problem with more and more points will converge to the solution of the original problem, which is this theorem actually. So yeah, don't look too much at the details, but these omegas are basically these sets that will get finer and finer, and you have a point in there, and this gives you the discrete problems, and we have strong convergence. And again, we need that there exists a function satisfying the constraints, but this time it's actually easier. We just need a complete Lyapunov functions. And the question again is, will we still get kind of a trivial solution which is just constant? And we can actually show, which is relatively easy, some statement. If the solution of your sorry, if the V naught is not constant, so you have a solution that isn't constant satisfying the constraints, then our solution of the minimization problem is also not constant. So at least you don't get the most trivial solution. How good it really is depends on the problem, and there's not much more you can prove in general terms. So we applied it again to our test problem from beforehand. So this is now this is again the Lyapunov function. You see it looks similar. Again, here's a minimum, here's a maximum of this periodic orbit, here's a minimum, and you can see the scale is even smaller now. So it's 10 to the minus 4, and the reason is that, yeah, I mean we're still we're minimizing the norm of V, so it wants to be as close to 0 as possible, but the thing that pushes it away from 0 is this this term in the cost function. But overall, it means that this the scale really is quite small. And this time I didn't actually plot V dot, but I plotted the points that are basically very close to 0. And you can see these two circles and the point. We also try to use it for the Lorentz attractor, which I've plotted just a numerical simulation in red. And in blue, you can see basically this set, but it's now in 3 dimensions, obviously, where the derivative of V dot is close to 0. And you get a pretty good, so this would be a set that's larger than that will contain the attractor, that will contain the chain recurrent set. And you can see that it matches the shape of the Lorentz attractor quite nicely. So I'm a bit quick, but that's all I wanted to talk about today. So just one other thing that I want to mention. So this whole framework of using Meshfree collocation for differential inequalities, we've used and motivated hopefully here with for complete Lyapunov functions. You can apply to other problems as well. For example, we've done it for non-smooth differential equations and a contraction metric. Basically anything where you want some differential operator on your function to be smaller or equal to 0, or have an inequality rather than equality, that's quite useful. Another application that we're currently looking at is switch systems, where you have a common Lyapunov functions for many systems at the same time, where you can't say it's equal to something, but it's really small or equal to 0 for many systems. And as I said, in this context, what I presented today, the thing that's still open and we very much would like to solve is to get some rate of convergence of these discretized to the continuous problems, because these theorems exist in the for the equation case, but we haven't been able to show it for the differential inequalities. We've done some numerical experiments, and it looks like there should be a rate of convergence. We're just not able to prove it. And these are some references. So I think I'll stop and happy to answer any questions that you have.
Yeah, thank you very much. Any questions or comments? Seems not.
Either it was far too complicated or too easy. I hope it was somewhere in the middle, but
Yeah, hopefully. Maybe it was very clear. So maybe I have a quick question. So how do you see, like, for example, this expanding to differential inclusions? I mean, how would you compare this to yeah, x dot is in capital F of x, and like, do you see that there is like a link there between set value dynamical system and differential inclusions, and finding Lyapunov functions for that versus this work that you are complete Lyapunov functions for differential equations?
That's a good question. It, I mean, if it's, it probably depends on on the right hand side basically. If it's just really if it say it was
just mostly the right hand side. I'm just trying to see
yeah
to
if it
think
was
in
an
terms of noise, right, on the right hand side, putting like noise on the right hand side, and then
yeah. I mean, if it was, if say the set would just be an interval, then you can obviously transform it into one inequality and then another inequality. So I guess it would be how can you formulate the problem in terms of inequalities?
yeah, in
So
this sense you
if the set
already
was a
have
polytope,
inequality.
basically,
Yeah, yeah.
you can easily get it into inequalities and get it in there. So I think that should be possible. Yeah.
Okay. Yeah, just
But
like
yeah.
thinking in terms of noise, like on the right hand side, and then you transform the noise into differential inclusion. So then
Yeah.
in that case, it will become your framework, and so the inequalities basically will
Mhm.
move from your stuff to the F itself, and then see what happens. Yeah.
Yeah, no, but yeah, that's a really good idea. Yeah, I guess, yeah, I guess you just need to get it into inequalities and, but I think that should work. Yeah, yeah.
Yeah, I have the impression that this kind of techniques would easily expand there, but I just want to see what you thought.
Hmm.
Yeah.
Yeah.
All right. Okay. Thank you. Yeah. Yeah. Last chance for people to ask questions. Yeah, it seems not. All right. Okay. Thank you. Actually,
I
there
may
might be two.
have
Yeah, there might be two people actually now.
Yeah, go on.
Yeah.
okay.
Yeah.
So I may have a very simple question that on something that I may have missed during the talk, but in the other minimization in which you minimize this integral involving p dot, you say that this pushes us out of zero, but I didn't quite get how.
Yes. So this one, you mean?
Yeah.
Yeah. So basically you can, so the idea would be that if, how can I say this? So I mean, this v dot here is either 0 or negative. So if you basically have a function that is, if you just have 0, the 0 function, then that would work here, but it would also give you 0 up here. I mean, the norm of v would be 0, v dot would be 0, everything would be 0. If you have a function where the derivative is negative, then this here is negative. This here would also be positive somehow, but because this is quadratic and this is linear, you can have basically something that is still overall negative, and that makes it kind of better than 0. Does that
Yes, thank you. So
make
I
sense? Yeah.
just yeah.
So
So I completely imagined some square there. So that's why.
yeah. So there's a square, yeah, which is and
No,
then the whole
in the
thing
v
will
dot.
actually be
So
negative.
I forgot it.
Yeah.
So I imagined that there was a square that turned into positive, but it was negative.
No, exactly. So this will really be negative. This will be positive, but overall the whole thing will actually be negative, but only slightly so. Yeah. Yeah.
I warned that it was a basic question.
Oh no, it's fine.
Thanks.
It's also, I mean, it's very quick, these slides, and there are quite lots of things on there.
I have also a question about the v dot,
Yes.
the derivative.
What it is, I noticed I should have put a formula there. So the formula is actually, I think it's in one of the pictures, very, very small. So the v dot, the form is actually gradient of v times f times the right-hand side. So that is the derivative along the solution. So it's basically, if you multiply this out, you can see it's a first order. So these are all the partial derivatives. Yeah, I apologize, it's really small. I should have put it on a much bigger. The gradient of v times f dot product with f is basically f1 times derivative of v in x1 direction and so on. So it's a first order partial derivative, or first order linear differential operator, this v dot here. Was that your question?
Yeah.
And I noticed I usually I think I deleted that slide somehow. I usually have a slide that gives the definition, and I think I thought I had too many slides, which I clearly didn't have, and I must have deleted that once. Sorry.
Yeah, because the row there is in high dimension, right? Like
yes, yeah. So the whole thing is, yeah, it could be in any dimension really, but yeah. So if it was just one dimension, this would still be kind of the normal derivative times f, but in high dimensions, it's the gradient f, gradient v times f. Yeah.
Okay, thank you.
You're welcome.
I also want to ask, what would happen if, for example, we consider H as an infinite dimensional Hilbert space?
That's also a good question. That's actually a good question. I mean, the H itself is an infinite dimensional space because it's a space of functions. So the H is infinite dimensional. The question would be, sorry, I thought you were saying if F was infinite dimensional. So basically you start with a PDE. I guess that becomes harder, but the H itself is a function space.
Is a function space. Also, how are you selecting for that degree so that we can minimize the function? Because we know that we have an infinite dimensional space. So what is the selection process so that we can try to?
The problem becomes kind of finite dimension because we discretize it with finitely many points. So that although this problem here is somehow in an infinite dimensional space, once we discretize it, we have n points, and then it somehow becomes something that's finite and treatable. If that does that make sense? Yeah. And the problem is that somehow the number of points, because it needs well, in the end you have these fill distance, so you need to fill your space with enough collocation points. So if it's a high dimensional space, you need more and more points. If it was so if this dimension here is very high of so the dimension of f basically, so the d here, if that's a very high dimensional space, the omega, then you need to have more and more points in there. But that's kind of makes it finite in some way.
Okay, thank you.
I have another question about the collocation point. So you choose it using the normal collocation points in the literature, or is there a particular choice you made for the collocation point?
Yeah. For these examples, in the end, I just took actually a regular grid of collocation. So basically, the error estimates work in a way that, as I said, the fill distance needs to be go to 0, and then so you could put scattered points wherever you want, but if you want to use as few points and have a small fill distance, then there's a way to do this in an optimal way, which is very regular. However, so that in these examples, that will be the first thing to do, to have quite a regular really grid of mesh points. If you want, I've also done some work to do it more cleverly somehow, because these are these iterations basically that I didn't really talk much about. So if you want to use fewer points, what you can do is you start with a regular grid but very coarse, and then you check whether the derivative, you want the derivative to be negative. And it will be -1, for example, when we fix it at the points, at your collocation points. If you have very coarse collocation points, then in between it will vary from -1. It will go up and down and so on. As long as it's not positive, it's fine. And you could basically start with a coarse grid, see where the derivative is negative. These are fine. Where it's positive, you just put another collocation point in to force it to be negative, or you're right on the right sign, and then you use these collocation points and iterate. So basically you make it denser and denser, but only in the areas where you really need it. So you can do an iteration on that, and that saves you lots of points. So it's a more clever way of choosing the points if you want to save points.
Yeah, thank you. That'll make really sense. Very nice. Thanks.
Thank you.
Last questions? Yes, here's someone. Itamar, did you want to ask a question or?
Yeah, I'm not sure about this question, but let me try.
Go for it.
The open problem of the rate of convergence sounds to me like a numerical issue, like numerical analysis issue, but maybe we can borrow from Lyapunov first, stability or instability. Intuitively, I tend to believe that we get good convergence in the stable case, but I may be wrong, of course. And I'm going even further, picking up example where we know the exact physics and the exact nature of the solution, and trying to figure out what the rate of convergence there, and maybe we can learn from the more difficult cases.
Yeah, I mean the rate of convergence is really, as you said, it's just the numerical bit. So it would, I mean that would be irrespective of the application to Lyapunov functions. So and let me go back to the slide. So it's really just how well do the solutions of this problem, the discretized problem, what's the error between those and the actual solution here? And that could be, I mean, this L might not come from a dynamical system at all. So I mean, it might be that for this application we can use some Lyapunov techniques to do that, but and it will depend on the fill distance basically, and it will depend on the kernel. I mean, that's what it does for the equations case, and just the way we construct our solution here, we haven't been. I mean, you've seen. I tried to show you in this proof how we try to link it to the theory with the equations, but we weren't able to use the error estimates yet. All we could do was the strong convergence, which is nice already, but we don't know how fast it converges to V.
I see. Okay, life is not always easy.
No, but that's fine.
Okay, that's why we are here.
Yes.
Thank you very much.
You're welcome.
That's a good philosophical conclusion for our talk, I guess. All right. Okay. Thank you. As I guess if there are no other questions or comments, okay, let's thank Peter again for the nice talk, and thanks everyone for coming, and see you all next week. Yeah. All right. Thanks, Peter.
Thank you.
Thanks. Bye. Bye.
Bye-bye.
Bye.